This video will cover the preparation of buffer solutions and their properties. Hydrogen number, or pH, measures a solution's acidity or basicity. It is defined as the negative logarithm of the hydrogen ion concentration. An acidic medium has a high concentration of hydrogen ions. A neutral medium has equal concentrations of hydrogen and hydroxide ions. A basic medium has a low concentration of hydrogen ions. The pH meter is used to accurately measure hydrogen number. It consists of a glass electrode with a thin bulb sensitive to pH. Another method to determine pH is by using test strips. All biochemical reactions require strict control over hydrogen ion concentration. Buffers help resist changes in pH. Buffers are solutions that resist changes in pH when small amounts of acid or base are added. They consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. Acidic buffers are made from a weak acid and its conjugate base, like the acetic acid and sodium acetate buffer. Basic buffers use a weak base and its conjugate acid, such as ammonia and ammonium chloride. When acid, or H+, is added to a buffer, the conjugate base, A-, reacts with it to form the conjugate acid, HA, minimizing the pH change. If base, or OH- is added, it reacts with the conjugate acid to yield the conjugate base and water, also resisting pH change. A buffer's ability to resist pH changes depends on the specific proportions of its two components. The buffer capacity is lost when one component is fully consumed. In the acetic acid buffer system, added acid reacts with acetate. Added base reacts with acetic acid. Both reactions consume the added ions, maintaining a stable pH. The Henderson-Hasselbalch equation is used to calculate and prepare buffers. It relates pH to the acid dissociation constant, pKa, and the concentrations of the conjugate base and acid. Buffer capacity is a measure of the buffer solution's efficiency in resisting pH changes. It's the moles of H+ or OH- needed to change the pH by 1 unit. It is directly proportional to the buffer's concentration. The practical part of this video will focus on the preparation of buffers. The objectives are to learn how to prepare phosphate buffer and to understand the behavior of buffer solutions. We will prepare 50 milliliters of 0.25 m phosphate buffer at pH 7.4 using monosodium dihydrogen phosphate and disodium hydrogen phosphate. The pKa is 7.2. The first step is to use the Henderson-Hasselbalch equation to calculate the required concentrations of the conjugate base, A-, and the weak acid, HA, which sum up to 0.25 m. The calculated concentration of the weak acid, HA, is 0.1 m, making the total concentration 0.15 m plus 0.1 m, which equals the target of 0.25 m. Next, calculate the weight in grams needed for A- and HA using molarity and volume. The required weight for A- is 1.065 grams, and for HA is 0.6 grams. Dissolve 0.6 grams of NaH2PO4 and 1.065 grams of Na2 hydrogen phosphate in distilled water. Check the pH and then bring the total volume to 50 milliliters using a volumetric flask. For the buffering test, measure the pH of 10 milliliters of the prepared phosphate buffer and 10 milliliters of KCl solution. Add 0.1 milliliters of 2-MHCl to both. Measure the pH again and record your observations.